videos at the very beginning. I don't know if you got the same shock I got. And he's picking up the chalk and he started smoking it. Of course, it's in the days when you could smoke chalk, isn't it? No longer allowed to smoke chalk. Anyway, this is another amazing guy, Peter Higgs. And I was looking at an interview that he gave the other day because he won the Nobel Prize with for the discovery of a mechanism that gives masses to fundamental particles. It's a very important mechanism. If it wasn't that mechanism, we'd be flying around at the speed of light. We wouldn't be here, we wouldn't exist. We wouldn't bind together. Particles don't have mass, they can't bind together. So it's quite an important mechanism. He discovered it. It was a number of people. And he was interviewed, and people are talking about him being the next Einstein, and he isn't like an Einstein, and he's saying absolutely no way, no way, no way. And he points out he did this work in the space of 3 weeks, and in the summer of 1964, he did the calculations, and he's saying Einstein took years and years and years and years to develop his theory. It shows you how thick Einstein is compared to Higgs. Einstein was doing this at some level a deeper thing, but what Higgs did was absolutely massive in the world of particle physics. And that's what I want to tell you a little bit about. And just to try and place it into context, without the Higgs mechanism, the mechanism that we'll discuss briefly, this wouldn't exist. All the rich structure that we're used to every day of our lives just wouldn't be there. In terms of this gallery, we get no pictures, we get no people, we have nothing to get us up in the morning. We wouldn't be here to get up in the morning. This is an important mechanism. Okay, that's what I want you to take home.
Can you speak a little bit louder?
No. You, Dimitri. So this is the standard model, nearly. I've wiped it out 2 big pieces. And it's complicated, but it's remarkable. Right? This is the called a Lagrangian. That's the L. SM means standard model, so you now know 3 of the terms. And this is a technique. If you can work out what this is actually simply you take the kinetic energy, the energy of the movement, and you take away from it the potential energy. That's called a Lagrangian. The energy of a system is usually the kinetic energy plus the potential energy. If you instead take away the potential energy, you get this thing. And this is the equivalent object with which we can describe the particles that make us up, make up the standard model. I'm not going to go into details with them, but I just want you to have a look at them and think about the symmetries of them. There's lots of beautiful symmetries. You know, there's the leptons, the things that we are made of, fermions in nature, the matter particles, are these combinations of these L's and these R's here. And you can see you've got an L here and an L here. And then you've got this funny B with a subscript. That's telling you how things change in time and change in space. That's giving you your kinetic energies. Then you've got these things, these W's with a U here, and the B's with a U here. These are going to be the force carriers. These are going to be the particles which transmit the forces, whether it be electromagnetism, whether it be the weak force, the reason why the sun burns. They're contained in here. And then you've got the same over here, and then you've got the quarks that are living down in this sector here that make up the nucleus of the atom. Now, this was the standard model. It was beautiful. It's beautifully symmetric. We love symmetry. And the next big message you need to have from the world of particle physics is symmetries are not good. Really, you want to break them. It's by breaking symmetries that actually you can get physically realistic things. That's happened so many times. And the problem that we have here with these symmetries is, it's okay, we're still on the Lagrangian. We've yet to reach the field equation. problems that we get here
Then spoil the end.
is that all the masses are zero. There is no mass to any particle. But we know that the fundamental particles have masses. You weigh something. So you weigh too much. But it's because of fundamental particles having their masses. And it's not present here. And one of the big problems that people were trying to address, and one in particular in the 1960s, they didn't really know, they didn't have a full standard model at the time of the Higgs mechanism. I should put it in the context of the time at which this was done. The Higgs mechanism came before the understanding of the standard model of particles. But what the Higgs mechanism did, it provided a method to give masses to all the particles. And the particular one that Higgs was after was the W particle, the one that mediated the weak interactions. It was known that that was only acted over a very short distance. Gravity acts over an infinite distance. Electromagnetism acts over an infinite distance. Because the particles mediating them are massless, it can easily propagate. It doesn't cost them any energy. The weak force acts over a very short distance. That was known. It was known that this particle that was represented here had to have a mass. But how did you consistently give this particle a mass and these remained massless? How could you do it in a way that kind of maintained the underlying properties that you expected your theory to have? And that was what Higgs was thinking about, and Engler and Brout was thinking about, and then Kibble and Ganat and Garalnik and who's the fourth? Hagen was thinking about. 3 separate groups, all at the same time, all wrote papers within the space of 4 weeks of each other. So what's this white bit missing? Well, this white bit is the bit that Higgs helped to come in. And so before I show it, let me just reiterate what the problem was. The problem is of mass. Okay? That the standard model has these symmetries present that prevent the particles having a mass. And yet we know that they have to have a mass. Because massless particles would move around at the speed of light. Atoms wouldn't form. The photon we know appears as massless, but we're made of stuff with mass. And the thing that provides the mass will turn out to be this new thing that Higgs and others came up with, the Higgs field. And it's therefore an extra component of the standard model. He added it in a very self-consistent way, but he added it in. Here's Higgs, here's his part of the Lagrangian, which is, you can barely see. And so here it is now. So the model describing you and me with the Higgs field phi. So here's the phi, this is the potential. Remember I said it's the kinetic energy minus the potential, gives you the Lagrangian. So there's the potential for this Higgs field. And now you can see that he's added in these terms here. You see how these fields, the W and this B field, have a phi multiplying them. Even if you don't know math very much, they're interacting. Yeah? They're affecting one another. And then if I come down here, these again are the leptons that I was talking about. The matter particles of which you and I are made of. The electron is the most famous one. They now have this phi in there. And what Higgs was able to do by introducing this in a self-consistent manner, he was able to provide a method by which these fields, these fermions, the matter fields, could acquire a mass, whereas they couldn't before. That was the key thing in this Lagrangian. You can buy T-shirts with this written on. So let me just kind of briefly tell you about the particle family, because it's incredibly simple. Right? There are what we call generations or families. There are 3 of them. I've labeled them with 3 different colors, okay? Within one family, there are 2 types of matter particles, or what we call fermions. There's a set that are called quarks. They make up the nucleus of the atom. The protons and the neutrons are made of quarks. In fact, they're made of up and down quarks. And then we have the leptons, the particles, and the most famous one of which is an electron. And then a third set of families, a fourth member of each family of these fantastic neutrinos. And Anne was talking about things that interact by just a weak interaction. Neutrinos do this. They've got no electric charge. So they're just passing through your body, millions upon millions upon millions every second. Passing through every square centimetre of your body, emitted mainly from the sun, coming through. They don't interact. So we have these particles. We have the up and the down. These combined make up the protons and the neutrons that we're made of. We have the electrons, which will then orbit around the protons and the neutrons, and then you've got your atoms. And different numbers of these protons and neutrons with different numbers of electrons give me the periodic table. So the periodic table is boiling down to this. And at its fundamental level in terms of what the particles are orbiting. And then you've got these, and we don't know. We know we need them, but we don't know why there are just these three families. These particles play basically no role in our everyday life. Why are they there? And in fact, for those of you that have seen the huge sizes of the particle detectors at CERN, at the LHC, if you've seen photographs of them, the reason why they're so damn big is because of that particle. Because that's the one that an experimental particle physicist will say, if one of those is produced, then you're entering the exotic world. Because this is our world. Right? We're here with our happy electrons and our happy protons. I don't know if you're aware of that, all particles are happy.
It's a strange.
And then you have the muon. And the muon is about 200 times heavier than the electron. Apart from that, it's got the same properties. When it gets produced, in order to produce a particle that's so massive, you need a lot of energy. So you fire the protons together in the LHC, smack them together, and every now and again you produce a muon. And what you're doing is you're moving yourself into this region, this exotic region. If you're in that region, you might well find new stuff forming, like dark matter. But the muon is so heavy, it's got so much momentum, it just shoots straight out of the detector. That's no good, but it's got a charge. And what happens to a particle in a magnetic field when it's got a charge? Audience participation. What happens? Yeah? Well, if a particle goes through a magnetic field, what do you think happens? I'll give you a clue. It bends. And by having a detector big enough, with a big enough magnetic field, you can actually begin to bend this muon. And in fact, the CMS detector bends it twice. So you have a really distinctive signature of this exotic particle being created, which they can use, the experimentalists can use as evidence of something really exciting has happened there. And let's go back and have a look at it. And so we've got these extra particles. We don't really know why there's just the three lots of families, but there seem to be. So these are the fermions. And then you have the bosons, the force carriers, that mediate the interactions between these matter particles. So we have electromagnetism. But because we're dealing with things on a very small scale, we think of them in their quantized, or packets of force being transmitted. So the packet of electromagnetism is the photon. The packet of the strong force, which binds the nucleus together, are called the gluons. Then you've got the weak force. This is the one that's transmitted by that massive particle. These are called the vector bosons. And then the one that's proving elusive, but which Dimitri's solving for up there, in that picture there, is gravity. Incorporating gravity into this picture. That's not yet properly been done. And then you have the antiparticles, related, equals and antis. So this has got just the opposite charge. then this Higgs particle, right, which is a boson. And boson just means, by the way, boson just means it's got an integer spin. Spin is a number that you associate with a particle. It's a very nice analogy with a spin. It's not an actual spin in terms of this thing spinning round, but you can associate it with it. And the bosons have an integer spin. So in other words, if you go around, you come back to the same point. A fermion has a half integer spin. A half integer spin means you have to go around twice to get to the same point. So if I'm a half integer, here's a half integer. Do I do this risky again? No. I'm looking at that glass and I'm a waiter and I do a half integer spin. I have to go around once and I have to go around again. And I'm back. Okay? That's what a half integer spin. Those are the fermions, and the bosons have integer spins. Now, we've mentioned these force carriers, and the property that they knew about in the 60s was that these were massless. That's perfectly consistent with the Standard Model, right? I've just told you the Standard Model, everything was massless. So the force carriers, it was known, the photon, the gluon, the graviton. Well, gravity isn't in the Standard Model, that's the problem, incorporating it into the Standard Model in a self-consistent manner. But it was, as far as we can tell, it's a massless particle. But it was known that this thing, that mediated the weak force, the decay of a free neutron that Anne mentioned takes about 6 minutes. It is about 800 seconds. What's that? Oh, it's a bit longer than 6 minutes. It's about 800 seconds. And that decay is mediated by the weak force, by this very massive particle. It has a mass of about 80 times that of a proton. And the question in the 60s was, why are the photon and gluon massless, yet the W and Z vector bosons are not? And how could you incorporate this self-consistently in this picture of the Standard Model, which seems to have everything massless? So do you get the idea that there was the problem? They knew that this particle responsible for the burning of the sun, that decay was mediated by a particle that was very massive. And yet they didn't know how to self-consistently incorporate that into their theory. And that was the goal at the time. And so they needed a mechanism to break this symmetry of the massless particles, to allow a particle to become massive, and thereby generate the mass. And this is what the Higgs boson was introduced to do, to explain this symmetry breaking. And so what Higgs proposed, as did the other people, was that empty space, as was mentioned in one of the excellent questions earlier, is not empty. It's full of particles, bubbling up and down in a vacuum. And in particular, it can contain a particular particle, or the particle, it turns out to be the excitation of something called the field. The fundamental quantity is the field. The field permeates everywhere, right? Like a temperature permeates everywhere. This is a Higgs field that's permeating everywhere. And it's the interaction of that field with the other fields which provide the masses of those fields and the excitations in those fields of the particles. So some particles, or excitations of the fields, move around unhindered in the presence of this Higgs field. They're the massless particles. They don't feel the Higgs field. An analogy I was thinking of coming in was fog. You know, there's some light which is impervious to fog. Like infrared wouldn't care, as far as I can tell that. If you were in a foggy region and you had an infrared camera, I don't think the infrared would get blocked out by fog. Is that right? Anybody know the answer to that? Am I wrong? Well, that was my. Whereas light clearly would, right? If you were far enough away in a foggy day, the light from your torch, the person trying to see it far away wouldn't be able to see it. And the infrared is like unhindered. So the fog is the Higgs surrounding you, and the infrared light is like the photon just propagating out, unhindered by the fog. But the light is the massive particle that gets stopped by the fog. And so the particles associated with these and other particles that are dragged back by this field. Another analogy that you sometimes hear is that the field is like a treacle. And if you drop something into this treacle, it slows right down. it picks up inertia as it's going through the treacle, interacting with it. And that, in other words, for inertia is mass. It effectively picks up a mass as it's trying to get through this field. And as it's now been discovered, and in fact, I should say it's now been discovered, so it may now be discovered. And the particle you associate with this field is the Higgs particle. So what people have actually discovered is a particle. So what is this particle? This field is there, it's fluctuating around. But imagine if you created enough energy so that you really excited this field in a small region. So the field got very, very high in terms of its value, its amplitude, and then came shooting back down and oscillated back and forth. Those oscillations then manifest themselves in quantum mechanics as particles. That's what the Higgs boson is. It's the particle associated with this field getting really excited and sloshing around. Why does it get really excited in the LHC? Because you fired sets of protons together at massive energies into an incredibly dense small region, and you've excited that region. So anything present in that region can absorb the energy associated with that collision. And the Higgs field is everywhere. So we have these fields that have been discovered. This is an analogy. In the 1980s, William Waldegrave, the science minister, so Margaret Thatcher was in power, he had a competition where he invited people to explain the Higgs mechanism. And I think they got bottles of champagne for the winners. Tom Kibble got one of the prizes, not surprisingly. Higgs didn't enter. So the analogy was, and they've replaced it here with Einstein, but the original image was actually Margaret Thatcher walking into a room. So all the people in blue, who are really Tory party members, they make up the Higgs field, filling the room, okay? And then in comes a particular particle that's going to interact with this Higgs field. It's Thatcher, in this case. In comes Thatcher, and then everyone swarms around her. And in swarming around her, they slow her down. She's no choice. And in slowing down, she's basically acquired a mass. She's come in with some particular momentum and been slowed right down. So she's acquired a mass. And then, this isn't such a good... The idea is this is the Higgs excitation itself, creating a boson. The idea is you get a rumour spreading, which I think means you put some energy into the system. Someone's shouting out some rumour, spreads, and then it just develops into this, as it does in the world of politics, into some highly excited region, and that's the Higgs boson itself. A particle like me, walking through, so what's a master particle in this analogy? Would be someone who these politicians have no interest in, walks into this room, and would just walk straight away through, because they wouldn't give a care in the world about that person. They wouldn't be trying to cluster around that person. Like that person would just walk straight through one. That's the massless analogy. So the key equation that we need then is E equals mc squared to understand how we create this Higgs boson. And I don't know how many of you have ever heard Einstein speak. So this is just a neat little thing of him speaking, explaining this equation.
It follows from the special theory of relativity that mass and energy are both different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Copeland and Walton in 1932 experimentally.
So that's Einstein explaining how, because of this c squared, C is 300 million litres per second. So that's 3 times 10 to the 7, 3 times 10 to the 8. I've got to square it. So that's 9 times 10 to the 16. So it's about a factor of 10 to the 17. So you can see that you can have a very small m, mass. It will get converted to a huge amount of energy. Okay. Through this amazing energy. So we have to build accelerators. Well, the UK began the very. You might laugh, but if you look at I don't know why you're laughing. We have here's the ring clearly. You can even have the prototype ring out there if you look carefully. To use the LHC. That's how we pre-accelerate particles. The Italians came close behind. Definitely don't know why Tom's laughing, because this is where they drop graduate students. I don't know if you've been. Have you been there?
Yes.
Right. That is really steep, and there's no protection. And then comes the LHC. Well, Anne showed this, so let's just move on. You can see the size of it. It's 27-kilometre ring with 4 key detectors. And the 2 that have made all the news are these 2, Atlas and CMS. These are what they call general purpose detectors. Their job has been to find the Higgs. That's been their primary job. The primary role of the LHC has been a success. It was to find the Higgs. That was the main thing that it was set up to do. And it's done it. So this is the detector, and well, some of this, this was me going down there. I thought you might like to see how excited I can be. But you'll also see the size of the detector. Remember what I was saying? Why it's so big? It's for that new one.
We're in. Cabin.
That's very funny.
Wow! Hey. This is it, it's the detector. We're here. And you've got the beam that comes in, and it goes into this monster. It's noisy. It's like if you've been on a ship across the English Channel or something, and you're on the hum of the engines constantly.
It's about at least 15 meters across, okay, and that same height as well, and about 25 meters long, with just detectors all over on one side. It's an amazing thing. Here's an event. The Higgs particle, when it's produced, is very massive. If you remember, I told you that the W particle is about 80 times the mass of a proton. The proton weighs about, in units that you're probably more familiar with, it's about 10 to the minus 27 kilograms or so. It's not measured in those units, you measure it in giga-electron volts. It's about a billion electron volts. The Higgs has been detected at 125 billion electron volts, 125 times the mass of the proton. It's highly unstable. It decays in a timescale of about 10 to the minus 24 seconds. So you never see the Higgs. They never see a Higgs. What you see is the byproducts. And in fact, this decay